In the profound and unbroken quiet of the cosmos, a silent and majestic expanse that stretches beyond the limits of comprehension, a solitary point of light, pale and blue, drifts through the eternal and infinite night. It is a mote of dust suspended in a sunbeam, a cosmic afterthought in the grand and indifferent architecture of the galaxy. Yet within its fragile atmosphere and across its dynamic surface unfolds the only known narrative of life in the universe. For billions of years, this world has been a sanctuary of ceaseless change, a crucible of transformation where the simple has given way to the complex, where chemistry has blossomed into consciousness, all within the vast and seemingly silent void. Its story is not written upon parchment, but in stone and fossil, in the layered sediments of ancient seas, in the magnetic minerals aligned in volcanic rock, in the isotopic ratios of gases trapped in glacial ice, and in the atmospheric whispers carried on the solar wind. It is a chronicle of breathtaking resilience and improbable stability, a saga of a planet that has continuously reinvented itself through cataclysm and calm. Yet every story, no matter how epic in its scope or profound in its detail, possesses an inherent finality, a concluding chapter dictated by the immutable laws of physics and the slow, tireless march of thermodynamic decay. We have long cast our anxious gazes upward, searching the skies for existential threats from the dark, the asteroid on a chaotic trajectory, the comet with its glittering tail of ice and dust, the nearby supernova poised to bathe the solar system in sterilizing radiation. But the greatest danger to this world, the ultimate architect of its demise, does not lurk in the cold interstellar depths. It shines down upon us every day, a nurturing presence turned eventual reaper. The very star that gave us life, that coaxed the first fragile self-replicating molecules from the primordial soup through its gentle, persistent energy, that powers every leaf through the miracle of photosynthesis and drives every storm through the differential heating of air and sea, holds within its radiant heart the seeds of our world's ultimate and inescapable unraveling. This is not a tale of sudden catastrophe, of a blinding flash or an instantaneous impact, but of a slow, inexorable, and majestic unraveling, a symphony of decline played out over time, scales that dwarf the entirety of human history, from the first stone tools to the latest quantum computer. We are about to run the tape of geological time forward, to project the future of our planet, not through the narrow lens of centuries or even millennia, but across the awesome, mind-bending expanse of a billion years and beyond. To witness how the gentle, steady brightening of our sun, a consequence of its own stellar maturation, will eventually shatter the delicate, interconnected balances that have made Earth a living world for eons, transforming it, step by inevitable step, into something utterly unrecognizable and ultimately silent. The question that hangs in the air, thick with implication, is not whether this will happen, for the astrophysics is clear and unambiguous, but how this process will unfold, in what order the pillars of our biosphere will fall, and what frail, tenacious forms might cling to existence in the deepening twilight. And in the face of this cosmic certainty, this destiny written in nuclear fire, we are compelled to ask, with a humility born of our newfound understanding, what, if anything, of this grand experiment in complexity will survive the coming furnace? And what does our knowledge of this end tell us about the value of our fleeting brilliant now? To understand the end, to truly grasp the magnitude of the processes that will one day render this world sterile, we must first pause and appreciate with renewed wonder the magnificent, dynamic, and improbably stable equilibrium that is Earth today. But a planet in constant conversation with itself, a complex, self-regulating system of staggering intricacy where geology, hydrology, atmosphere, and biology are not merely neighbors but inextricably linked co-conspirators in a 4-billion-year dance. The ground beneath our feet, which feels so solid and permanent, is in truth a thin, fractured crust, a jigsaw puzzle of colossal plates, some bearing continents, others forming the deep ocean floor, all adrift on a viscous, convective sea of semi-molten mantle rock. This process, known as plate tectonics, is the planet's great internal engine, its primary architect and landscape sculptor. It is the force that builds mountains, that scrape the sky, that carves ocean trenches that plunge into lightless pressure, that forges island chains from volcanic fury. It recycles the very substance of the crust, drawing old, cold, waterlogged rock down into the fiery mantle at subduction zones and belching forth new mineral-rich land from volcanic vents and the spreading ridges that stitch the seafloor together. This relentless, cyclic motion, driven by the heat left over from planetary accretion and the ongoing decay of radioactive elements deep within the core, is responsible for the very shape of our continents, the distribution of our metal ores and fossil fuels, and the long-term climate patterns we experience. It is a process that has been ongoing in one form or another for over 3 billion years, with no sign of cessation, a testament to the energetic youth of our world. The world map we memorize today, with its familiar shapes of Africa, the Americas, Eurasia, and Australia, is but a single frame in a film of staggering length, a snapshot of continental positions at one fleeting moment in geological deep time. Rewind the reel far supernough, and you would find all the continents clustered into a single monstrous landmass known to geologists as Rodinia, a supercontinent that straddled the equator over 1 billion years ago. Fast forward from that ancient past, and you witness its breakup and the subsequent slow, majestic drift that led to another aggregation, the more familiar Pangaea, which dominated the planet some 300 million years before our time. The Earth's surface is not a fixed stage upon which the drama of life plays out. It is itself a performer, engaged in a slow, fluid, and immensely powerful dance of stone, a ballet measured in centimeters per year, but with consequences that resonate across eons. This geological dance, this grand tectonic choreography, is intimately and crucially tied to the climate through a feedback loop of profound elegance and importance: the carbonate-silicate cycle. This cycle is Earth's built-in planetary thermostat, a regulatory system operating on million-year timescales that has maintained surface temperatures within a range conducive to liquid water and thus to life for the vast majority of our planet's history. It begins not with life, but deep within the planet's interior, where the immense heat of radioactive decay and residual gravitational energy from its formation melts rock into a viscous, mobile magma. This magma, rich in dissolved gases, including water vapor and carbon dioxide, rises through fractures and weaknesses in the crust. When a volcano erupts, whether in a cataclysmic explosion or a steady, effusive flow, it does far more than spew ash and lava onto the surface. It exhales. It releases vast quantities of carbon dioxide, a potent greenhouse gas, into the atmosphere, replenishing what has been lost. There, high in the sky, the carbon dioxide mingles with water vapor, forming a weak carbonic acid. This slightly acidic rain then falls upon the continents, weathering the silicate rocks, the granites, the basalts, the feldspars that constitute much of the continental crust. The chemical reaction is a slow, relentless consumption, a geochemical digestion. The carbonic acid breaks down the tough silicate minerals, liberating ions like calcium and magnesium and creating soluble bicarbonate. These dissolved components, these elemental building blocks, are then carried by rivers, the planet's great circulatory system, down to the waiting sea. Upon reaching the ocean, these ions become the fundamental feedstock for a vast array of marine life. Countless organisms, from the microscopic, intricate shells of coccolithophores that cloud the water in massive blooms, to the mighty colonial architectures of coral reefs, incorporate the calcium and bicarbonate into their protective shells and skeletons, crafting them from solid calcium carbonate. In doing so, they perform a critical act of planetary engineering. They draw the carbon, originally from the volcanic atmosphere, out of the water column and solidify it into biological architecture. When these organisms die, their calcified remains, trillions upon trillions of them, rain down upon the seafloor like a constant, ghostly snow, accumulating over millennia into thick, pale layers of sediment. Over deeper eons, under the weight of subsequent deposits, these layers are compressed, dewatered, and cemented into solid rock, the limestone that forms our cliffs, the chalk of our downs, the marble of our sculptures. This is a crucial transfer, a locking away. Carbon dioxide from the atmosphere has been captured by rain, transported by river, utilized by life, and finally imprisoned in stone on the ocean floor, a geological sequestration of monumental scale. But the magnificent cycle is not yet complete, for Earth is a world of relentless motion. The great conveyor belt of plate tectonics ensures that the oceanic crust, with its cargo of carbonate rock sediment, is eventually pulled back into the mantle at the deep oceanic trenches that mark subduction zones. There, in the intense heat and crushing pressure of the descending slab, the carbonate rocks break down once more. The carbon dioxide is re-released, percolating upward through the overlying mantle wedge, where it helps to melt the rock, creating new gas-rich magma that will feed future volcanic systems, ready to be breathed out once more, beginning the grand cycle anew. This magnificent planet-spanning loop acts as a stabilizing governor on Earth's climate. It prevents a catastrophic runaway buildup of carbon dioxide that would trap solar heat relentlessly, boiling the oceans and transforming our world into a hellish Venusian greenhouse. Conversely, it also prevents all carbon dioxide from being permanently sequestered in rock, which would starve the atmosphere of this greenhouse gas, plunging global temperatures and locking the planet into a global, lifeless icebox, a snowball state. It is a delicate, self-correcting, negative feedback system that has maintained temperatures within a habitable, albeit fluctuating, range for billions of years, allowing life not only to persist, but to evolve through epochs of great change, through snowball Earth events and hothouse periods. The entire biosphere, from the deepest root to the highest leaf, is not a mere spectator, but an active participant in this grand geochemical ballet. Plants and microorganisms accelerate silicate weathering by breaking rock apart with their roots, by secreting acidic compounds, and by altering soil chemistry, thereby increasing the rate of carbon drawdown. Their evolution, particularly the rise of vascular land plants in the Devonian period, which pumped vast amounts of oxygen into the air and drew down carbon dioxide through both photosynthesis and enhanced weathering, changed the very rhythm and sensitivity of the cycle itself. Life and the planet are not separate entities. They are co-authors, deeply intertwined, of this ongoing, multi-billion-year story. The atmosphere we breathe, the climate we experience, the very composition of the oceans are all products of this relentless cyclic dialogue between the living and the lithospheric. Yet, for all its robustness and elegant self-regulation, this magnificent system operates within a set of parameters dictated by an external master, a benevolent dictator whose own nature is slowly changing, the sun. Our star is the ultimate source of the energy that drives Earth's weather systems, fuels the photosynthesis at the base of our food webs, and even subtly influences the rate of the carbonate-silicate cycle itself. Warmer global temperatures, which can be caused by an increase in solar output, accelerate the chemical weathering of silicate rocks, pulling carbon dioxide out of the atmosphere at a faster rate. For now, over multi-million-year timescales, volcanic outgassing from plate tectonics keeps pace with this drawdown, maintaining the balance. But the sun is not a constant, eternal flame. It is a dynamic, aging fusion reactor, a massive ball of plasma whose internal structure is undergoing a slow but relentless metamorphosis. Its slow stellar evolution will, with the certainty of a ticking clock, eventually overwhelm Earth's intricate capacity to compensate. The stage is thus set not for a sudden dramatic cataclysm from without, but for a gradual, unstoppable, and fundamental shift in the very rules of the game, a shift driven by the changing heart of our parent star. The Earth's systems are robust, but they are not infinitely flexible. They exist within a window of conditions, and that window is slowly, inexorably being closed by the very light that opened it. To project our world's future, to chart its descent from a blue marble to a barren orb, we must first look to the immediate geological destiny already written in the slow, creeping trajectories of the drifting continents. Based on the current vectors, measured with astonishing precision by satellite lasers and understood through the fundamental principles of plate tectonics, we can sketch with reasonable confidence the physical geography of 100 million years hence. The Atlantic Ocean, born from the rift that tore the supercontinent Pangaea apart some 200 million years ago, is still widening at a rate comparable to the growth of a human fingernail, pushing the Americas further from the coastlines of Europe and Africa. But elsewhere on the globe, convergence and collision are the dominant themes. Africa, a continent slowly splitting along the East African Rift Valley, a future ocean in the making, will see its northern portion continue its relentless march northward. It will collide with southern Europe, a process already beginning today in the complex geology of the Mediterranean, ultimately closing the ancient Mediterranean Sea, a body of water with a history stretching back to the time of the dinosaurs. The tectonic forces at this colossal collision zone will be titanic, mirroring the ongoing collision of India with Asia that produced the Himalayas. The sedimentary layers of the Mediterranean seafloor, along with slices of oceanic crust and fragments of continental margins, will be thrust upward, folding, fracturing, and metamorphosing into a new mountain range of Himalayan proportions. This Mediterranean mountain range could stretch from the Strait of Gibraltar all the way to the Persian Gulf, its snow-capped peaks in a future cooler climate potentially rivaling or even exceeding the height of Everest, a new spine across the face of the Old World. The Red Sea, a young ocean in its infancy, will be pinched shut by the northward movement of Africa and the clockwise rotation of Arabia, which will be sutured firmly to the Asian mainland, ending its independent journey. In the vast basin of the Pacific, the story is one of relentless compression and subduction. The Australian continent, drifting steadily northward, will plough into the complex, fragmented island chains of Southeast Asia. The intricate archipelagos of Indonesia and the Philippines, a product of ongoing tectonic chaos, will be compressed further, their islands crushed, amalgamated, and uplifted into another formidable mountainous belt, a continuation of the alpine Himalayan chain that will then girdle a significant portion of the equatorial and mid-latitude globe. On the opposite side of the Pacific, the westward movement of the North American plate will see the fragment of crust carrying Baja California and a slice of Western California currently riding on the Pacific plate slide northward along the San Andreas transform fault, eventually colliding with the southern Alaskan coast. This oblique collision will crumple the continental margin, giving rise to a new steep cordillera along the western edge of North America, a newborn mountain range to replace the ancient Rockies. Those ancient Rocky Mountains, born of a much older collision, will have been reduced by hundreds of millions of years of wind, water, and ice to gentle rolling hills, their mineral wealth scattered and their roots exposed at the surface. The planet's face is being remade, its familiar features erased and new ones sculpted by forces of such immense power and patience that they pay no heed to the transient kingdoms of life flourishing upon its skin, oblivious to the borders of nations and the memories of species. This grand reshuffling of continents, however, is far more than a mere cartographic curiosity or a subject for speculative future atlases. It has profound and inescapable consequences for global climate patterns and the destiny of life itself. Ocean currents, the great thermal regulators and nutrient distributors of the planet, are dictated almost entirely by the arrangement of land masses and the shapes of ocean basins. The modern global conveyor belt, or thermohaline circulation, where cold, dense, salty water sinks in the North Atlantic and Nordic seas and drives a deep, slow current that circulates oxygen and nutrients around the world's oceans, depends on very specific configurations. A connection to polar regions and particular basins that facilitate downwelling. As continents merge and strategic seaways close, such as the possible closure of the Indonesian throughflow or the constriction of the Atlantic, this global circulatory system can be severely disrupted, throttled, or even shut down entirely. In a future world where the Atlantic is narrowed by the converging Americas and Afro-Eurasia, or where the aggregation of a new supercontinent creates a single vast world ocean, Panthalassa-like, with limited connections to polar regions, oceanic stagnation becomes a real and present danger. Without vigorous deep water formation and the oxygenation it brings, the ocean's depths become anoxic, devoid of life-giving oxygen, a condition that allows sulfate-reducing bacteria to thrive, producing toxic hydrogen sulfide. This is a proven recipe for a mass extinction. The geological record is unequivocal on this point. Such oceanic anoxic events, often linked to periods of high volcanic activity and warm climates, have been the silent, suffocating killers of the past, wiping out vast swaths of marine life, as seen at the end of the Permian period, the greatest extinction event Earth has ever known. The land, too, suffers under the new geography dictated by plate tectonics. The interior of a massive supercontinent is far from the moisture-giving oceans, its climate dominated by continentality. It becomes a dry, extreme place, a continental desert or arid steppe where temperature swings between day and night and between summer and winter are violent and rainfall is scarce and unpredictable. Life is pushed to the margins, to the narrow coastal fringes and the more temperate polar realms, leading to a fragmentation and reduction of habitable area on a planetary scale. This logical progression of continental drift leads us inevitably to the world of 250 million years from now. Based on the seminal work of geologists like Dr. Christopher Scottis and his influential Pangaea Proxima model, the slow, stately dance of the tectonic plates reaches another grand culmination, another moment of global aggregation. The Atlantic Ocean, having stopped its expansion, will begin to close. The subduction zones that currently fringe the Pacific Ocean may migrate, or new ones may form along the eastern coasts of the Americas, a process for which there is some evidence in the geological record of past supercontinent cycles. As the Atlantic oceanic floor continues to be subducted beneath the Americas or Africa, the ocean itself begins to close, a mirror image of its own birth from the rift in Pangaea. The Americas are drawn eastward back toward Africa and Europe in a long, slow embrace. Africa, having long since collided with and become sutured to Europe, is part of a merged Afro-Eurasian landmass, a single colossal continent. The slow, inexorable convergence brings the Americas into contact with this megacontinent. The Atlantic closes, its mid-ocean ridge extinguished, its basin disappearing. From the south, Antarctica may also join this aggregation, driven by larger-scale mantle currents, and Australia, having long since collided and merged with Asia, is fully integrated into the whole. The result is Pangaea Proxima. The next all-Earth, a new supercontinent in the cyclic rhythm of assembly and dispersal that has characterized our planet for billions of years. Its configuration is predicted to be a distorted, messy reassembly, not a neat, compact mass. Some sophisticated computer models suggest South America will curl around the southern tip of Africa, colliding with it and potentially cradling a remnant inland sea, a last, dying and increasingly saline echo of the once mighty South Atlantic. This new supercontinent, Pangaea Proxima, is a planet of climatic extremes, a world of brutal simplicity in its geography, leading to profound harshness in its environment. Its vast, uninterrupted interior, stretching thousands of kilometers from any coastline, is a hyper-arid desert, a sun-blasted badland where summer temperatures could regularly exceed 55 degrees Celsius, a heat that would challenge even the most adapted xerophytic life. Rainfall is episodic and savage when it comes, delivered by powerful but rare monsoonal systems, carving deep flash flood canyons in the parched earth, before the water quickly evaporates or percolates away, leaving behind only dry washes and salt pans. The only regions with reliably temperate, life-sustaining climates are the narrow coastal strips, where maritime influences moderate temperatures, and the high-latitude areas near the poles, which may experience seasonal warmth but avoid the extreme desiccation of the interior. The circulation of the atmosphere itself is fundamentally altered by the monolithic landmass. Large, permanent high-pressure systems establish themselves over the supercontinental interior, stifling cloud formation and perpetuating the aridity. The global ocean, while vast, is likely to be thermally stratified and in its depths anoxic and lifeless, a stagnant, sulfidic reservoir. The combination of intense climatic stress, catastrophic habitat loss, and fragmentation for both marine and terrestrial ecosystems, and the breakdown of oceanic nutrient cycling would likely trigger a major extinction event, a slow, grinding decline over millions of years, driven not by an impact from space or a sudden volcanic paroxysm, but by the very architecture of the planet itself. the consequence of its own internal heat engine. This is a world that would still be rich with life compared to the barren future to come, but it is a life under siege, constrained, specialized, and struggling, a stark preview of the greater solar-driven trials that lie ahead in the deep future. While this tectonic drama unfolds on the surface, a quieter, more insidious, and far more consequential change is accelerating in the heavens, a transformation in the very source of light and life. Our sun, that seemingly immutable and eternal beacon in our sky, is undergoing its own profound and inevitable metamorphosis. It is a main sequence star, a G-type yellow dwarf, powered by the nuclear fusion of hydrogen into helium in its searing 15 million degree core. This process, which has provided steady energy for 4.6 billion years, is not static. As hydrogen nuclei fuse through the proton-proton chain, they create helium nuclei, an inert ash that settles in the star's heart. Helium, with 2 protons and 2 neutrons, is denser than hydrogen. Over millions of years, this accumulating helium core very gradually contracts under its own weight, growing ever so slightly hotter and denser. This gentle contraction increases the gravitational pressure, which in turn raises the temperature and pressure of the remaining hydrogen fuel in a shell surrounding the dense helium core. Nuclear fusion reactions are exquisitely sensitive to temperature. A small increase can cause a dramatic exponential rise in the reaction rate due to the quantum tunneling effects described by the Gamow peak. Therefore, as the core contracts, the rate of hydrogen fusion in the surrounding shell actually increases. This counterintuitive result means the sun is gradually, inexorably growing more luminous, outputting more radiant energy every century, every millennium, every million years, a slow brightening written into the laws of stellar physics. The numbers involved are vanishingly small on human or even historical scales. But they are relentless, compounding over geological time. The sun's luminosity increases by roughly 1% every 100 million years. This is not a linear process. It is believed to accelerate slightly as the core becomes richer in helium and the fusion shell becomes thinner and hotter. Within the next 500 million years, stellar models predict the sun will be approximately 5 to 6% brighter than it is today. To Earth's intricately balanced climate system, this is a monumental shift, a significant perturbation to the energy budget of the entire planet. That additional watt per square meter of solar flux warms the atmosphere and the surface layers of the oceans. It invigorates the hydrological cycle, leading to greater evaporation and potentially more vigorous, energetic weather patterns, more powerful storms, and more intense precipitation events in some regions. But its most critical long-term impact is on the planet's built-in thermostat, the carbonate-silicate cycle. The increased global temperature resulting from the brighter sun accelerates the chemical weathering of silicate rocks, the first step in the carbon sequestration process. The slightly acidic rain works faster on the exposed rock surfaces. Rivers carry a greater load of dissolved calcium, magnesium, and bicarbonate ions to the sea. Marine organisms living in a warmer, potentially more stratified ocean may also precipitate carbonate shells at a different rate, though this is complex and dependent on ocean chemistry. The net geochemical effect, however, is clear. Carbon dioxide is being pulled from the atmosphere and locked into carbonate rock at an accelerated pace, driven by the increased temperature. Ordinarily, over multi-million-year timescales, volcanic outgassing from plate tectonics would eventually replace this drawn-down carbon dioxide, maintaining the balance. But the rate of global volcanism is tied to the pace of plate tectonic recycling, which operates on its own, internally driven timetable governed by mantle convection and crustal rigidity. It cannot instantly ramp up production to compensate for the increased drawdown forced by the external stimulus of a brighter sun. The result is a growing imbalance. The atmospheric concentration of carbon dioxide begins a long, slow, but irreversible decline, dipping ever lower as the weathering thermostat struggles to cool a planet being heated from above by an increasingly powerful furnace. This marks the beginning of the end for one of Earth's greatest and most beautiful evolutionary innovations, complex, multicellular plant life as we know it. The seemingly lush, invincible, and vibrant green mantle of our planet, the forests, the grasslands, the flowering meadows, harbors a critical biochemical vulnerability, a flaw written into the very ancient chemistry of its dominant form of photosynthesis. Photosynthesis is the foundational alchemy of life on Earth, the sublime process that captures the intangible energy of sunlight and transforms it into storable chemical energy, building living tissue from air and water. For the vast majority of plants, the towering trees, the waving grasses, the colorful flowers, the crops that feed humanity, this process follows a metabolic pathway known as C3 photosynthesis. It is an ancient system evolved in the Archean or early Proterozoic eons when atmospheric carbon dioxide levels were many times higher than today. It relies on a remarkable but notoriously inefficient enzyme called ribulose 1,5-bisphosphate carboxylase oxygenase, or Rubisco, to capture carbon dioxide molecules from the air. Rubisco, however, is a flawed tool. It is enzymatically slow, limiting the maximum rate of photosynthesis, and it is prone to a critical error. It cannot perfectly distinguish between carbon dioxide and molecular oxygen. In an oxygen-rich atmosphere like Earth's, Rubisco frequently mistakenly grabs an oxygen molecule instead of carbon dioxide, initiating a wasteful and energy-consuming process called photoperspiration, which actually releases previously fixed carbon and costs the plant valuable energy. To operate effectively and outcompete this oxygen-catching mistake, C3 plants require a relatively high concentration of carbon dioxide in the atmosphere. They exist perpetually in a delicate balance between the carbon they fix through photosynthesis and the carbon they lose through respiration and photoperspiration. When the gains equal the losses, a plant reaches its compensation point. It survives, metabolically treading water, but does not grow. To thrive, to build wood and leaf and fruit, it needs a surplus, a positive carbon balance. As the sun brightens over the coming hundreds of millions of years and carbon dioxide levels fall due to enhanced silicate weathering, that precious surplus for C3 plants steadily diminishes. According to sophisticated models in fields like astrobiology and planetary ecology, within about 500 to 600 million years, atmospheric carbon dioxide concentrations will dip below a critical threshold, estimated to be around 150 parts per million, and then continue to fall. For C3 plants, this is catastrophic. At such low concentrations, photorespiration overwhelms productive photosynthesis. The Rubisco enzymes spend more time binding oxygen than carbon dioxide. Growth stutters, then stops. Seedlings fail to establish mature trees struggle to repair tissues. Forests, the great towers of cellulose and lignin that took hundreds of millions of years to evolve their dizzying complexity, begin to falter. First, the most sensitive and specialized species vanish. Then, whole ecosystems unravel from the bottom of the food web upward. The great coniferous boreal forests and the diverse deciduous forests of the mid-latitudes retreat, wither, and die. Grasslands, dominated by C3 grasses, follow suit. The land, over a period spanning tens of millions of years, begins to brown, its verdancy fading like an old photograph exposed to light. This is not a sudden explosive event, but a protracted botanical apocalypse, a slow-motion unraveling of the primary producer base for nearly all complex terrestrial life, strangled by a lack of the very gas it once, through its own evolutionary success, helped to scour from the air in ages past. Yet, life is ingenious, and evolution has already provided a preview of a potential escape route, a biochemical workaround to this coming crisis. Another form of photosynthesis exists, the C4 pathway, evolved more recently, likely multiple times independently, in response to declining carbon dioxide levels and increasing aridity during the Cenozoic era. It is a clever, energy-intensive biochemical pump. C4 plants, including many of our most important crops, like maize and sugarcane, as well as numerous warm-climate grasses and certain desert shrubs, use a two-step process to concentrate carbon dioxide around the rubisco enzyme. They first fix carbon into a 4-carbon molecule in mesophyll cells, then shuttle this molecule to bundle sheath cells, where the carbon dioxide is released in a localized, high-concentration environment, effectively feeding the rubisco enzyme a rich diet and virtually eliminating the problem of photoaspiration. This adaptation allows them to photosynthesize efficiently at atmospheric carbon dioxide levels as low as 10 parts per million or even less. As the great C3 forests die back over millions of years, the hardier, more efficient C4 grasses and shrubs may expand their range, dominating the new, harsher and drier landscapes of Pangaea Proxima. They will form sparse, tough scrublands, savannas of resilient survivors, a world of subdued greens and browns, of plants optimized for water conservation and low carbon dioxide survival. They represent a potential extension of complex macroscopic plant life for several hundred million years beyond the demise of the C3 empires, a final tenacious chapter in the story of botanical life on Earth. But even these masters of adaptation are living on borrowed time, for the sun's brightening is a relentless crescendo with no peak in sight, and the challenges will soon extend far beyond atmospheric chemistry into the realm of raw thermal survival. By the time 1 billion years have passed into the future, the sun will be over 10% brighter than it is in our current epoch. The consequences of this increased solar flux are transformative and severe, pushing Earth's systems beyond the breaking points of complex life. Climate models, while varying in their precise predictions due to uncertainties in cloud feedbacks and biological responses, paint a consistent and sobering picture of a world under intense and escalating duress. The global average surface temperature could soar to 45 or even 50 degrees Celsius, turning currently temperate regions into uninhabitable heat zones. The polar ice caps, having likely been absent for hundreds of millions of years due to the overall warmer climate, are now warm themselves, possibly featuring temperate, ice-free oceans. The tropics are infernal, with sea surface temperatures potentially exceeding 40 degrees Celsius, temperatures that would disrupt marine ecosystems and drive hypercyclones of immense power. The increased heat drives evaporation at a furious, unsustainable rate. The oceans, while still present in vast quantities, are hotter, more stratified, and thus less able to circulate oxygen to the depths, leading to expanding oceanic dead zones. The global water cycle becomes more extreme and erratic, with powerful evaporation from the superheated tropical oceans leading to torrential monsoon-like rains in certain convergent zones, while the vast continental interiors of Pangaea Proxima become permanent, hyper-arid deserts, larger and more severe than any in Earth's past. Daytime temperatures in these continental deserts could regularly exceed 70 degrees Celsius, a heat that would instantly denature proteins and cook the cells of any large complex animal life venturing into the open. The atmosphere itself undergoes a fundamental chemical change. With the collapse of the vast C3 forests and the severe reduction in overall plant biomass, the great planetary engine of oxygen production, oxygenic photosynthesis, is critically impaired. Atmospheric oxygen levels, no longer replenished at scale, begin a long, steady, and irreversible decline as free oxygen reacts with surface rocks, volcanic gases, and reduced minerals in the ocean, gradually being removed from the air. For animal life, the combination of extreme heat stress, catastrophic habitat loss, collapsing food webs, and oxygen depletion presents an insurmountable suite of challenges. Large-bodied creatures, with their high metabolic demands, limited surface area-to-volume ratios for cooling, and greater oxygen requirements, are the first to vanish. The intricate food web, already frayed and simplified by the loss of plant diversity and productivity, collapses entirely. Herbivores starve for lack of viable vegetation. Carnivores and scavengers, in turn, find their prey base disappearing. The age of animals, a spectacular, creative explosion of form, behavior, and consciousness that began in the Ediacaran and Cambrian periods over 500 million years ago, draws to a sorrowful and protracted close. The world becomes quieter, its soundscape diminishing. The skies, once filled with the calls of birds and the buzz of insects, empty. The seas, while still containing microbial life and perhaps some simple, resilient multicellular organisms like sponges or certain worms, grow still, devoid of fish and whales. The only macroscopic, complex life remaining might persist in scattered refugia, deep, extensive cave systems, where temperatures remain stable and humidity is high, isolated, high-altitude plateaus where the air is cooler and denser, or perhaps in specialized, sheltered polar environments if any liquid water and moisture remain. But these are dying pockets, isolated arcs on a planet-wide flood of heat, genetic diversity dwindling with each passing generation. The main stage of Earth's biosphere, the domain of large, active multicellular life, is retreating irrevocably to the microscopic, to the world of bacteria and archaea that ruled the planet for its first 2 billion years. The oceans, Earth's great blue heart, the cradle of all life, now face their own existential crisis, one that strikes at their very existence as a surface feature. The brightening sun does not just warm the oceans, it ultimately threatens their continuous presence on the planet's surface. We tend to think of the oceans as a permanent, defining feature of our world, but on geological timescales, they are transient participants in a dynamic exchange. Water is constantly being cycled between the surface reservoir and the mantle at subduction zones, Oceanic crust carrying hydrated minerals, clays, serpentines, is carried down into the Earth's hot interior, locking away water in the mantle. Conversely, at mid-ocean ridges and volcanic arcs, new water is outgassed as steam from magma replenishing the surface. This is a slow, deep Earth cycle, but over billions of years, its net effect matters significantly for planetary water inventory. Furthermore, in the upper atmosphere, a more direct and permanent loss mechanism operates: ultraviolet photodissociation. High-energy ultraviolet photons from the Sun can break water vapor molecules apart into hydrogen and hydroxyl radicals. The lightweight hydrogen atom, if it reaches the exosphere, can achieve escape velocity and be lost to interplanetary space forever. This is a slow, relentless leak that over eons can drain a terrestrial planet of its surface water, a process believed to have played a major role in desiccating Mars. But the more immediate and dramatic threat to the oceans in the time frame of 1 to 2 billion years hence is the specter of a runaway greenhouse effect. As global surface temperatures climb past certain thresholds due to the ever brighter sun, the rate of evaporation from the oceans increases non-linearly. Water vapor itself is a potent greenhouse gas, far more effective molecule for molecule than carbon dioxide at trapping infrared radiation. As more water evaporates into the atmosphere, it traps more outgoing heat, which in turn raises surface temperatures further, which causes even more evaporation. This is a powerful positive feedback loop, a vicious cycle of self-reinforcing warming. There exists a critical theoretical threshold, a point of no return, often called the moist greenhouse or runaway greenhouse limit, where this cycle becomes self-sustaining and will continue until the planet's surface water inventory is either entirely in the atmosphere as a superheated steam or through photodissociation lost to space. For Earth, with its deep, abundant oceans, this process would be slow, perhaps spanning hundreds of millions of years, but once that threshold is crossed, it would be unstoppable by any natural planetary mechanism. The sky would thicken with dense, global clouds and steam, the surface atmospheric pressure would rise dramatically, and the global average temperature would soar well past the boiling point of water at sea level. The oceans would not boil away in a dramatic, rolling frenzy as in a pot on a stove. They would simmer, then steam over many millions of years, their global mean level gradually lowering, retreating from the continental shelves, leaving behind vast, exposed continental interiors that were once seafloor. During this long parching agony, the geography of water undergoes a mournful transformation. Vast shallow seas, the inland epiric seas that once covered continents, evaporate completely, leaving behind immense, blinding, mineral-crusted salt flats, the spectral, desiccated ghosts of ancient oceans. The last vestiges of liquid surface water retreat to the deepest ocean trenches, the lowest points on the planet, and to the polar regions, which may still be marginally cooler. These become the final, isolated bastions, super salty, anoxic, and boiling lakes under a thick, hot, permanently overcast sky of steam and clouds. Concurrently, a profound geological change begins. The lubrication provided by water in the crust, which lowers the melting point of rocks and facilitates the sliding of tectonic plates, becomes scarce. Rocks become drier, more rigid and stronger. The great engine of plate tectonics, which has run for over 3 billion years, begins to seize, its motions slowing as the mantle itself dries out and the crust becomes a single, rigid lid. Subduction slows, then grinds to a halt. Volcanism, fueled primarily by the recycling of water-rich crust and mantle melting, dwindles to a trickle. The planet's geological heartbeat, the pulse of quakes and eruptions that renews the surface, grows faint and irregular. Earth transitions from a dynamic, multi-plate planet to a one-plate, stagnant lid planet, much like Venus or Mars today. Without tectonic renewal to build new mountains, the landscape grows ancient and tired. Erosion by the fierce winds and the occasional acidic rain continues its work, but without mountain-building orogenic events to counter it, the continents are worn down over eons to low, monotonous plains, a global peneplain. Impact craters from asteroids and comets, no longer erased by tectonic recycling, subduction, or the erosive power of abundant liquid water and life, begin to accumulate on the surface, pockmarking the ancient cratered crust like the face of the moon. Isolated, massive shield volcanoes may still form over lingering mantle hotspots, creating singular, giant volcanic domes, but they are the last, infrequent flickers of a dying geological fire. The atmosphere, now devoid of life's balancing influence, no photosynthesis to produce oxygen, no vast forests to mediate humidity and carbon, undergoes a final, deeply ironic transformation. With oxygenic photosynthesis extinct, atmospheric oxygen plummets to trace levels consumed by oxidation reactions with freshly exposed reduced minerals on the barren surface and with volcanic gases like hydrogen sulfide. The dominant atmospheric gases become water vapor in immense quantities during the runaway greenhouse phase, and as the last volcanoes sputter out their final exhalations, carbon dioxide once again returning to its primordial dominance. Earth's atmosphere begins to resemble a primordial, or perhaps more accurately, a post-biotic version of its sister planet Venus, before Venus's own runaway greenhouse took full hold. Thick, stifling, predominantly carbon dioxide, and searingly hot. The surface temperature, driven by the ever-brightening sun and the powerful water vapor greenhouse, climbs past 100 degrees Celsius, then 200, then higher. The last polar lakes, the final repositories of surface liquid water, finally evaporate completely. The final, tenacious chapter of surface life on Earth belongs not to plants or animals, but to the true champions of endurance, extremophile microbes. These microscopic entities, descendants of lineages that have survived in Earth's harshest environments for billions of years, could persist in the most hostile niches imaginable, in deep underground aquifers of superheated, mineral-rich water where geothermal heat provides energy via chemosynthesis. Deep within crystalline salt crusts, where they enter a state of suspended animation, a cryptobiotic stasis, for millennia, or perhaps floating in the cooler upper layers of the thick atmosphere, surviving on trace chemicals and ultraviolet energy, much as some astrobiologists have speculated could be possible in the temperate cloud decks of Venus. They are the last heirs to a 4-billion-year dynasty of life clinging to a dying world. But even these ultimate survivors have a limit, a threshold of temperature and desiccation beyond which not even their robust biochemistry can function. Approximately 2.8 billion years from the present, according to some integrated stellar and climate models, the Sun will be approximately 28% brighter than it is today. The Earth's surface temperature, even at the poles and in the theoretical shade, will likely exceed 150 degrees Celsius. The atmosphere is a dense, soupy fog of superheated steam and carbon dioxide, with surface pressures many times higher than today. The crust is bone-dry, irradiated by a fierce, bloated-looking sun glaring through a perpetually hazy, hot sky. In these ultimate conditions, the final microbial refuges fail. The deep subsurface biosphere, cut off from any chemical energy gradients connected to the photosynthetic past, slowly starves as its geothermal energy sources wane and its chemical substrates are exhausted. Any atmospheric microbes are ultimately scorched by the increasing heat or fall through the atmospheric layers into the lethally hot, lower atmosphere and surface. One by one, the last living cells, the final threads of the tapestry of life, perish. The chemical disequilibrium that is the definitive, unambiguous signature of life, the strange, persistent, unstable mix of gases like oxygen and methane coexisting in an atmosphere that should have long since reacted to equilibrium, finally fades away. The atmosphere settles into a dull, predictable, and boring chemical equilibrium dominated by carbon dioxide and water vapor, with perhaps traces of nitrogen and inert gases. Biosignatures vanish. If an interstellar probe from another civilization, equipped with sophisticated spectrometers, were to fly through the solar system at this distant future date, its sensors would detect a rocky planet with a thick water vapor and carbon dioxide atmosphere, scorching hot, geologically stagnant, and utterly, unequivocally dead. There would be no hint in its atmospheric spectrum, no whisper in its thermal profile, that this world once rang with the songs of whales, rustled with the leaves of mighty forests, felt the footfalls of dinosaurs, or glittered with the electric lights of cities and the campfires of a curious species. All memory, all physical trace of that vibrant living past is erased by thermodynamics and time, sanded away by the relentless increase of solar flux. Yet, astonishingly, this sterile Venus-like future is still not the final act for Earth as a physical object. The Sun's evolution as a middle-aged star is only approaching its midpoint. For billions more years, it will continue its slow brightening on the main sequence, until it exhausts the hydrogen fuel in its core. Around the 5 to 7 billion year mark from the present, the Sun will begin its dramatic and violent death throes. Having fused all the hydrogen in its core into helium, nuclear fusion will cease there. The core, now a compact ball of inert, electron-degenerate helium, will no longer have the outward radiation pressure to support itself against its own immense gravity. It will contract violently, heating up to phenomenal temperatures of around 100 million degrees Celsius. This sudden intense heat will ignite a shell of hydrogen fusion around the now quiescent helium core. The sudden infusion of new energy from this shell-burning phase will cause the Sun's outer layers to expand to monstrous, grotesque proportions. It will leave the stable main sequence and ascend the red giant branch, first becoming a subgiant, then a full-fledged red giant star. Its luminosity will increase by a factor of thousands, its radius will swell, potentially out past the orbit of Venus, perhaps even reaching or gently grazing the orbit of Earth. The inner solar system will be engulfed in a tenuous but searingly hot stellar atmosphere, an expanding sphere of rarefied gas that will fundamentally alter the dynamics of the inner planets. The precise fate of Earth during this stellar expansion has been a subject of intense scientific debate and refined calculation over the decades. As the Sun loses a significant fraction of its mass through powerful stellar winds during its red giant phases, its gravitational grip on the planets weakens. According to Newtonian mechanics, the orbits of the planets would consequently expand, migrating outward. Early calculations provided a sliver of hope that Earth's orbit might migrate outward just enough to escape the swelling photosphere. The visible surface of the red giant Sun, leaving Earth as a scorched, molten cinder orbiting outside the star's visible disk. However, recent, more sophisticated studies incorporating complex tidal interactions and analyses of data from planet-hunting telescopes like NASA's Transiting Exoplanet Survey satellite, which have surveyed stars at various evolutionary stages, paint a grimmer and statistically more likely picture. These surveys have looked for close-in planets around stars similar to the Sun in its red giant phase. They find a notable absence of such planets, suggesting that stars like our Sun are remarkably efficient at engulfing or destroying their inner planetary children during this turbulent phase. The process is likely a combination of tidal forces, the drag and friction from the Sun's extended, diffuse outer layers acting on the planet, and complex orbital decay dynamics, which can pull the planet inward even as the star's mass decreases. The delicate balance of forces needed for a graceful orbital escape appears to be lost more often than not in the chaotic dance of mass loss and tidal interaction. Thus, in roughly 7.6 billion years from now, at the peak of its red giant phase during the helium burning period, the Sun's radius will reach its maximum extent, likely extending to about 1 astronomical unit, or even slightly beyond. 1 astronomical unit being the current average distance from the Earth to the Sun. Earth, having spent over 8 billion years as a living world and then a dead one, will find itself immersed within the outer tenuous layers of its parent star. The planet will not be vaporized instantly in a flash, but will be subjected to intense heating from the surrounding plasma and enormous drag forces from the dense stellar envelope. Its crust and mantle will melt, then vaporize. Its iron core will be liberated, dissolving into the stellar mix. The material that once constituted mountains and oceans, continents and fossils, the bedrock of civilizations and the bones of dinosaurs, will be dissolved, diffused, and homogenized into the stellar plasma of the Sun's expanding envelope. Earth will cease to exist as a distinct, coherent object, its unique geological and biological history erased at an atomic level, its substance becoming one with the star that gave it birth, completing a profound circle of stellar ecology. The Sun's red giant phase is, cosmically speaking, a brief, brilliant, and violently destructive finale to its 10 billion-year stable life on the main sequence. After a few 100 million years of expansion and instability, including a phase of violent helium shell flashes known as the thermal pulses, it will become unstable, pulsating and ejecting its entire outer layers into space in a series of majestic, explosive paroxysms. This ejected material, enriched with heavier elements like carbon and oxygen forged in its core during the helium burning phase, will expand outward, forming a beautiful glowing planetary nebula, a cosmic hourglass or butterfly of multicolored gas and dust, illuminated by the fierce ultraviolet radiation from the exposed, incredibly hot stellar core now at its center. At the heart of this ephemeral nebula, shining with a stark blue-white light, will remain the Sun's core, now exposed as a white dwarf, an Earth-sized sphere of degenerate matter. Composed primarily of carbon and oxygen, unimaginably dense, a teaspoonful would weigh several tons, initially searingly hot at over 100,000 degrees Celsius, but possessing no internal fusion. It is a stellar ember, a fading cinder of what once was. Over trillions of years, this white dwarf will slowly cool and fade, radiating its residual heat into the blackness of space, eventually becoming a cold, black dwarf, a dark crystal in the void, though the universe is not yet old enough for any such objects to exist. The beautiful planetary nebula will disperse over tens of thousands of years, its atoms joining the interstellar medium, enriching it with the elements for future generations of stars and planets. The outer planets, Jupiter, Saturn, the ice giants Uranus and Neptune, if they survived the red giant's violent winds and gravitational perturbations, will continue to orbit this darkening cinder in a perpetual frozen twilight. Their icy moons, perhaps briefly, warmed during the red giant phase, but then returning to a deeper cold than ever before. The story of the solar system as a dynamic family of planets orbiting a vibrant star is over, its material legacy scattered and waiting to be incorporated into new cosmic stories. This is the narrative dictated by the cold, elegant equations of astrophysics and geology, a timeline of inevitable stellar evolution and planetary decline, a fate shared by countless worlds in the galaxy. Yet, the short contemplation we began with contained a crucial qualifying phrase, a wild card inserted into the deterministic deck, assuming no human intervention. And here, at the precipice of this seemingly inexorable cosmic fate, we must pause and consider the implications of this wild card, the unprecedented variable of technological consciousness. Humanity, or whatever intelligent, self-aware, tool-making descendant we may evolve into over the coming millennia and eons, represents a force without precedent in the 4.5 billion-year biological history of Earth, an agent capable of foresight, of long-term planning spanning generations, and of technological manipulation on a scale that progresses from the planetary to the stellar. We have already, in our brief geological moment, begun to rewrite nature's local story in profound and often reckless ways. We have diverted great rivers, leveled mountain ranges for their minerals, altered the composition of the global atmosphere through industry and agriculture, and reshaped the biosphere through extinction, domestication, and transplantation. We have done this largely clumsily, reactively, as a young and often short-sighted species still learning the rules of the complex system we inhabit. But this is merely our adolescence. What might we, or our successors, achieve with another million years of cultural, scientific, and ethical evolution? A million years is a mere heartbeat in the billion-year timelines we have been discussing. Yet it is an ocean of time for the development of intelligence and technology. The challenges laid out by astrophysics, continental drift and its climatic consequences, the declining carbon dioxide for plant life, the solar brightening, the eventual ocean loss are, from a certain perspective, merely engineering problems of the grandest imaginable scale. Could a future civilization, possessing mastery over matter and energy that we can barely glimpse, stabilize the tectonic plates through some form of deep geophysical management, perhaps by modulating mantle convection with precisely deployed energy sinks or sources? Could they artificially regulate global atmospheric chemistry on geological timescales, supplementing carbon dioxide for remaining plant ecosystems or manufacturing oxygen through planetary-scale industrial processes to maintain a functional biosphere long after the natural geochemical cycles have failed. Could they construct vast orbital sunshades, a swarm of trillions of lightweight, adaptive mirrors positioned at the stable Lagrange point between Earth and the Sun, to deflect just enough of the increasing solar flux to keep the global climate temperate, effectively moving the planet into the shade? Such megastructures, concepts once confined to the realm of science fiction with names like stellar engines or Dyson swarms, are now being seriously contemplated by physicists and futurists as theoretical possibilities for a sufficiently advanced Type II civilization on the Kardashev scale. This is the realm of stellar engineering, or astroengineering, the application of technology on a scale that matches the forces of stars themselves. Perhaps the solution is not to fix Earth in its orbit, but to move the planet itself. Far-fetched as it sounds to our contemporary minds, theoretical mechanisms have been proposed, such as using repeated, meticulously calculated gravitational assists from a series of carefully guided asteroids or comets passing close to Earth, to gradually nudge its orbital trajectory outward over millions of years, keeping it within the continuously moving habitable zone as the Sun brightens. This is a project requiring astronomical precision, immense patience, and control over celestial mechanics, a task for a truly long-term, stable civilization thinking in geological time. Alternatively, a future humanity may choose a different, perhaps more likely path entirely: dispersal, a biological and cultural diaspora. We may become a multiplanetary species within our own solar system, then an interstellar one. The colonization and terraforming of Mars, the cloud-top habitats of Venus, the construction of vast, habitable orbital colonies around Jupiter or Saturn, using resources from their moons, or the launch of self-sustaining generation ships sent on millennia-long voyages to other star systems with promising exoplanets. These are all visions that could ensure the survival of Earth-originating life, consciousness, and culture long after the homeworld has become inhospitable. In this expansive scenario, Earth becomes a cradle, a revered museum, a sacred origin point to be studied and remembered, visited, but no longer solely relied upon for survival. Its eventual geological and stellar fate, while poignant and emotionally resonant, would not be the final fate of our lineage. The story would continue elsewhere under different suns. There is a deeper, more philosophical and existential layer to this contemplation, one that transcends engineering solutions. Our existence, as a conscious species aware of its own origins and its ultimate fate, is a transient spark in the immense cosmic dark. All composite things, from stars and galaxies to planets and life forms, have a beginning, a middle, and an end. The second law of thermodynamics, the increase of entropy, guarantees it. The universe moves from states of order to states of disorder, from concentrated energy to diffuse heat. To rage against this cosmic tide is to misunderstand the fundamental, beautiful, and tragic nature of reality. The unique beauty and profound tragedy of the human condition, and perhaps of any advanced consciousness, is that we are aware of this finitude. We can project our minds across billions of years, using the tools of science, and foresee the end of our world and even the death of our star. This knowledge is a heavy burden, a form of Promethean fire, but it is also a singular gift. It defines, in the starkest possible terms, the precious, fragile, and fleeting nature of the here and now. It lends an ultimate urgency to our exploration, to our quest for understanding, and to our stewardship of the brief, shining window of planetary habitability we have been granted. The Earth, in its physical form, will not last forever, but the story of life and awareness that began in its oceans and on its continents may have chapters yet unwritten on distant worlds under alien suns, carrying forward the narrative of curiosity and wonder that defines us. And if, against all odds and hopes, we do not survive to see these distant epochs, if humanity, or any successor intelligence that arises from the tree of life, succumbs to its own internal flaws, to resource depletion, to self-inflicted catastrophe, or to a random cosmic accident like a gamma-ray burst or a large impact long before the billion-year markers are reached, then the meticulous, awe-inspiring narrative we have just traced, the decline of forests, the parching of oceans, the sterilization of the surface, will play out on a silent, unobserved, and uncomprehended stage. The forests will fall without a witness to mourn them. The oceans will steam away into an empty, indifferent sky. The sun will swell and consume a planet bearing only the faint, weathered, and radioactive ruins of a civilization turned to dust eons prior, its monuments sandblasted to nothing, its digital records dissolved into thermal noise. There is a profound and necessary humility in accepting this possibility. It places our contemporary achievements, our artistic triumphs, our scientific discoveries, and our political follies in their true cosmic context. We are a local phenomenon, a beautiful and complex pattern that spontaneously emerged from the laws of physics and chemistry on one small rocky world among trillions. Our meaning, our purpose, is not bestowed upon us by a silent universe. It is created by us in the connections we forge, the knowledge we uncover and share, the art and music we create, and the love and compassion we share during our fleeting moment in the sun. We are the universe's way of understanding its own beauty and its own tragedy. In the very end, we are confronted with a cosmic poetry that is both humbling and uplifting. We are, as the astronomer Carl Sagan famously reminded us, literally made of star stuff. The carbon atoms that form the backbone of our DNA, the oxygen that fills our lungs, the iron that carries oxygen in our blood, the calcium in our bones, all were forged in the nuclear furnaces of massive stars that lived and died violent deaths in supernova explosions long before the Sun and Earth were born. Their explosive deaths seeded the giant molecular cloud that eventually collapsed under gravity to form our solar system. We are not merely inhabitants of the cosmos, accidental tourists in a vast universe. We are a physical manifestation of the cosmos, a way for the universe to know itself, to reflect upon its own existence, to contemplate its own origins and destiny. Our consciousness is the universe becoming self-aware, and when the Earth is gone, swallowed by the dying red giant sun, our constituent atoms, the very atoms that once composed living beings, mountains and oceans, will be returned to the stellar furnace. They will be scattered once more into the interstellar medium by the beautiful planetary nebula. There, they will mix with other elements, eventually becoming part of a new molecular cloud, condensing into a new generation of stars, and perhaps coalescing into new planets around those stars. The grand eternal cycle of stellar birth and death, of planet formation and destruction, of the recycling of heavy elements continues on these vast timescales. Our physical essence, the stuff of our being, is immortal in this grand impersonal recycling. We came from stardust, forged in stellar alchemy, and to stardust we shall return, our atoms destined for future worlds and perhaps future lives. It is a closure that is not a true end, but a transformation, a reuniting with the ancient cosmic process that gave us birth, a return to the source from which all things emerge. So, as we sit in the quiet of our own time and contemplate the deep future of our pale blue dot, this fragile oasis of life we call home, we are left not with despair, but with a powerful and complex mixture of awe and responsibility. Awe at the epic scales of time and space, at the majestic, impersonal forces of nuclear fusion and plate tectonics that shape worlds and stars over billions of years. And responsibility, a deep, moral and practical responsibility for the brief, shining sliver of cosmic time that is ours. The Holocene epoch and whatever follows it, a period where the planet remains lush and habitable, a garden in need of tending. Our responsibility is to understand this world with ever greater clarity, to protect its delicate, intertwined systems from our own short-sighted actions, and to perhaps, one day, if we mature in wisdom as we have in power, to gently guide the fate of our world, or to carry its precious legacy of life and consciousness to the stars, becoming gardeners not just of Earth, but of life itself in the cosmos. The story of Earth, from its fiery accretion to its silent, sterile future, is a testament to change, to resilience, and ultimately to impermanence. It is a story that will one day conclude, as all stories must, but within this grand epic, the human chapter, the chapter of questioning, of looking up at the stars with wonder and daring to imagine their future and our own place within it, of using reason and empathy to build meaning, is perhaps the most remarkable part of all. It is a story still being written, its next lines, its next verses, waiting to be chosen by the generations to come. The cosmos is vast and old beyond measure, and our time within it, on this world, is precious and brief. Let us use it wisely, with courage, with compassion, and with eyes wide open to the magnificent reality of our situation. Good night.